Pleasant day, everyone. Welcome to our session for today. So today we are going to focus our discussion on the rate of change. So this topic is more on the applications of the derivative. But before we go to the details, so let us have first the learning objectives of this topic. Okay, so this topic has these learning objectives. So number one is determine a new value of a quantity from the old value and the amount of change. And the second one is calculate the average rate of change and explain how it differs from the instantaneous rate of change. And then apply rates of change to displacement, velocity, and acceleration of an object moving along a straight line. Then predict the future population from the present value and the population growth rate. And use derivatives to calculate the marginal cost and revenue in a business situation. Alright? And since this topic is also a very long topic, so I'm going to divide the whole topic into 3 or 4 videos, separate videos. Okay? Now let's go back to what we had discussed before when we have the geometric representation of the slope. So we talked about before the slope of the tangent line to the curve at the point P, and it is given by this expression. Alright, so we have slope of the line is equal to the limit of the slope of the line PQ. Actually, this line PQ is the secant line as Q approaches to P. And this is equivalent to the limit of the slope of the secant line PQ as x approaches to A. And this is equivalent to the limit of f of x minus f sub A divided by x minus A as x approaches to A. Okay, so I will show you later how this expression arrive into this form. Now, when f of x is defined in an open interval containing A, the tangent line to the curve y equal to f of x at the point with coordinate A and f sub A is the abscissa of the point P, and f of A is the ordinate of point P, which is the value of the function at x equal to A, is the line through P with slope given into this form. That slope equal to the limit of f of x minus f of A divided by x minus A as x approaches to A. Okay, so to understand more about this, I will show you the graph, how this expression is being derived. So the condition here, class, is that provided that the limit exists. Okay, so if the limit exists, then we have this slope. Alright, so we have this graphical representation, class. So here in our graph, we have point Q and point P. Okay, so we have this line that intersect the curve, our curve or function, that is the graph of the function. So this is our function y equal to f of x. So the line that crosses at 2 points on the curve or intersect at 2 points on the curve is what we call the secant line. So this line here, okay, this is what we call secant line. it intersects at least 2 points on the curve. So this is what we call secant line. And a line that intersects at 1 point on the curve is what we call the tangent line. Okay? So if we let A be the distance from the y-axis towards that point, we called it A, distance from the y-axis to that point P. So it's the same as we put A here. Alright, so it means that this A here is the distance from the y-axis towards that point P. Similarly, if we let the distance from y-axis to point Q, if we let that distance equal to x, so we can also put this one here x. So that indicates that x here is the abscissa of this point Q. Now for the height or the distance of the point P from the x-axis, that is equivalent to the value of the function at x equal to a. So value of y, value of y equal to the value of the height of the function, which is y, equal to the value of the function when x equal to a. So therefore, this is this distance here. This is our f sub a, and we put it here as f of a. Okay, so this means that this one is the distance from the x-axis towards that point P. Okay, so that is our f sub a. Similarly, the distance from the x-axis towards point Q, so this distance, so that is x, that is the value of the y when x equal to x. So this is our f sub x. This is the value of the function at this point at x equal to, so in this case our x equal to x, so we have f of x. So it means that this one, f of x, is the height of the function at this point Q. Okay, that is the value of our y at this value of the distance from y-axis to that point x. So this is the corresponding value, or this is the corresponding value of the y when x is equal to that value here. Alright, but our x is also equal to x, so we just substitute. In other words, class, we just substitute the whatever is the value of x here to our function. So like here, we have y equal to f of x as x when the value of x is equal to a, so the value of the function is f sub a. Now using the same function expression as the value of x is equal to x, so substituting x to the x here, so this is the same, so f of x. So this is the value of the function at x equal to this, which is also x. So that's why we have f of x. So the meaning of that is f of x is just the height. No, this is the height of the point Q from the x-axis. So it means this is our f of x. All right, and our f of a. So this is our f of a, height from the x-axis. So this is our f of a. So similarly, when we say distance from y-axis towards q, that is x, so this is also x here, right? So this is also x, and I said a while ago that the distance from the y-axis to that point P equal to a, which is that one, so that is also equal to a. Alright, now the difference, so the difference of the heights, so this one, so what is the difference? or the chains, so we just subtract, no, this is the height, okay, this is the height of Q from the x-axis, and this is the height of P from the x-axis. Then this is the change is just the difference, so this is simply F sub x minus F sub A. Okay, and similarly, this is the distance. X is the distance from Y to point Q, and A is the distance from Y to point P. So the difference of these distances, so it means this one. So the distance from P to Q, horizontal distance from P to Q, is just the difference of the distance from Q and the distance from y-axis to Q and the distance from y-axis to P. Or simply, this is just, if this is A here, if this is A, then minus this, if this is X and this is A, so this distance is just X minus A, right? This is just, so this one here, this is just X minus A, and similar to this one, this is also our X minus A. Alright, now as mentioned, that the slope, so the slope, remember the slope in our definition and also in our first two videos that was uploaded, we still apply class the definition of the slope from our analytic geometry. We have M is equal to rise over run. Okay, we can still use this one here. So in this case, if you look at this, so the slope of the secant line PQ, right? So we have in our one of our slides a while ago is something like this. This one. Okay, so we have here limit of the slope of the secant line, which is PQ. PQ, that is the line PQ. This is the secant line. Okay, so the limit of this as x approaches to A. Okay, so this is slope equal to the limit of the slope of PQ as Q approaches P. So it means as Q approaches P means if you move this point Q towards point P, so what will happen? Okay, so from our graph, we can say that as you move this point Q, so assuming that point Q is here, if that is now our new position of our Q, okay, so our Q is moving on that position. So we have now the secant line. This is now the new position of our secant line. Okay, so originally we have this triangle class. So before Q moves in this new position, so we have here the triangle, right? We have formed this triangle. Okay, and we have a definition that slope is just the rise over run. So in this case, this is our rise. Okay, this is our rise, and this is our run. Alright, so for this particular position of Q. Now, as Q moves at this point, along this curve, along this graph. So if this is now the position of our Q, point Q, so what happens? Okay, so this will be our new triangle. So we have now formed a new triangle here. Okay, so this is now the new triangle. Alright, so this is our new triangle. So in this case, so this is now our rise. So this is our new rise. Okay, this is our new rise. Then this is our new run. Then as point Q moves further, so moves again here. So this is our new position of our Q. Okay, so Q is moving. So what will happen is that we have now the new position of our Q, and this is now the resulting triangle. So we have another triangle. So this is now the secant line. So the new position of the secant line is something like this, right? So our secant line, so again this is our secant line. So our secant line also moving in this direction, class. Alright, it's moving in that direction, our secant line, as Q moving towards P or approaching P. So this is now our new rise, and this is our new run. Okay, this is our new run. So what did you notice? So before the point Q moves, so we have this triangle. Okay, so we have this triangle as big as this. Alright, so this is our Q here, and this is our P. Alright, and this is our rise, and this is our run. Okay, now as Q moves towards P or approaching P, so our next triangle becomes like this, right? And this is now our new rise, and this is our new run. And as Q, this is our Q here, this is our Q, and this is our P. And as our Q moves closer and closer to P, so what happens? So we have now this is now the resulting triangle. Okay, so we have our P here. So we have our P here, and this is our Q, and this is now our new rise. No, this is our new rise, and this is our new run. Okay, so that's why in our expression here we have the slope. No, the slope of the secant line is the limit of the slope of PQ. So the slope is equal to the limit of the slope of the line PQ, which is the secant line, as Q approaches P. So as Q approaches P, you see our Q is moving towards P, so it's approaching P. Alright, it's approaching P, and as it approaches P, so what happens is that the difference x minus a also shrinking, so x is moving towards A. So you can see that our x is moving towards A, right? So x is approaching A, x approaches A. Alright, so we have here, it says that when f of x is defined in an open interval containing A, so what is our open interval here? Our open interval is A, this is the open interval, class, this one, A to x. So it means this is our open interval. This is the value, or this is the interval where our x is changing or decreasing towards A. Alright, as Q moves from this initial position towards P. Okay, now what is the limit? So the limit of the slope of the secant line, which is PQ, okay, if you look at this figure, and if you look at this, so the limit of the slope of the secant line PQ, remember this is our PQ, original position of PQ, right? This is our original position of PQ before it moves, and as it moves to this point here, so this is now the new position of our secant line, and as it moves farther at this point, this is now the position of our secant line. And what is the limit of this position? So it means that if Q approaches very, very close to P, or exactly at P, so that's the limit now. As Q approaches P, then the secant line approaches the tangent line. So this is the limit. So the limit of secant line is the tangent line. So that's why we have here the limit of the slope of MPQ as x approaches to A equal to the limit of f of x minus f of A divided by x minus A as x approaches to A. Alright, so it says that when f of x is defined in an open interval containing A, the tangent line to the curve y equal to f of x at point P with coordinates A and f of A is the distance from y-axis to the point P, and f of A is the height of the function at point P, is the line through P with slope. So this is the expression of the slope equal to the limit of f of x minus f of A divided by x minus A as x approaches to A, provided that that limit exists. Okay? So I hope you understand this explanation, class. Now we have here so further to what I have mentioned a while ago. So in this section we return to the problem of finding the equation of the tangent line to a curve y equal to f of x if P coordinates A and the value of the function at A, or f of A, is a point on the curve y equal to f of x, and Q having a coordinates of x and f of x is a point on the curve near P. Then the slope of the secant line through P and Q is given by this. So remember, this is the slope of the secant line. MPQ, or the slope of the secant line PQ, equal to f of x minus f of A divided by x minus A. So this is our what we call the rise, and this is the run. Alright? That is the rise and that is the run. Okay? Now in our we have here a sample problem. So find the equation of tangent line to the curve. So we're given here the function y equal to square root of x at P coordinate 1 and 1. So this is our A and this is our f sub A, or this is the value of the function at x equal to A, which is x equal to 1. So in our definition, what we have reviewed in our derivation, so we have the slope is equal to the limit of f of x minus f of A divided by x minus A equal to, so I'll show you the right side of this equation later on. So the equation with tangent line to the curve at point P, coordinates 1 and 1. So the limit, alright, so the limit from our derivation, so the limit in the definition that was discussed a while ago can be written as follows. Right, we have the slope equal to the limit of f of x minus f of a divided by x minus a as x approaches to a. And we can also let this x sub a, x minus a, meaning the difference of this horizontal distances, we can let this be equal to h. Okay, so if you let this be equal to h, then you will have x becomes a plus h. So we change x to a plus h, then minus f of a, so that remains f sub a. Denominator, since we change x to x plus a, so the denominator becomes h. So why it becomes h? So why it becomes h? So it's just something like this. So we let h be equal to x minus a, the difference. So we have originally f sub x minus f sub a divided by x minus a. So the limit of this as x approaches to a. So this is our m. Okay. So now when we let h equal to x minus a, so this becomes m equal to the limit of f sub our x minus a is, so x, this becomes, so you have to solve for x here, so this becomes h plus a, you transpose a there, so equal to x, so change x to h plus a, so this is h plus a, alright, then minus f sub a, then divided by, so x minus a is equal to h, as h, this time as h approaches to 0. Okay, so that's why we have this expression, limit of f sub h plus, or that is just the same, no, because that is addition. So you can rewrite this also as the limit of, you can interchange, this is just a sum, so you can write a first plus h, just to be consistent to our graph, over h as h approaches to 0. So this is our other expression of our slope. Okay, so we have here that this limits, okay, gives the slope of the line tangent to the curve y equal to f of x at p, having this coordinate a and the value of the function at x equal to a, if the limit exists. So again, the condition is that if the limit exists. So the slope of the tangent line to the curve at a point when it exists is sometimes called the slope of the curve at that point. So the y values on the curve near the point are close to corresponding y value on the tangent line. Okay, so I hope you understand this one, class. Now let's have, before we go to the example, let's take this concept first. So next we have what we call amount of change formula. So amount of change formula. So one application for derivatives is to estimate an unknown value of a function at a point by using a known value of a function at some given point. So together with its rate of change at a given point. If f of x is a function defined on an interval a plus h, so a is the abscissa, a plus h is the ordinate, then the amount of change of f of x over the interval is the change in the y values of the function over that interval. Okay, so what does it mean? So it means, class, that you see here, as q moves along this curve, so you see this is the difference. This is the difference in y value, f of x minus f of a, this is the difference. Alright, so as it moves, as q moves down to this point and going closer to p, so we can see that this change in y value, or the y also changing. Okay, so it changes. So the amount of change of f of x over the interval is the change in the y values, so meaning the height and the y values of this difference of the function over that interval. So what interval? So this interval, class, from a to x in this case. Or if we let h, if we let h be equal to x minus a, okay, if we let this one equal to h, so we let this be equal to h, alright. So the amount of change of f of x over the interval is the change in the y values of the function over that interval, and it is given by f sub a plus h minus f of a. So we have from here, since x equal to, we let x h equal to x minus a, then we can transpose it to other side, so we can solve for x. So our x here is a plus h. So we can write here as f sub a plus h minus f sub a. Okay, so they're just the same when you let h be equal to x minus a. Okay, so we have therefore this given expression that f sub a plus h, f sub a plus h minus f of a, so we can let this be our equation 1. So this is the amount of change. This is the amount of change of f of x. Then we have the average rate of change. So what is this average rate of change? So the average rate of change of the function f over the same interval is the ratio. The ratio of the amount of change. So we have the amount of change, which is this one. Ratio of the amount of change, which is this one, over that interval. So what is the interval? That is h, because we let this interval, this is the interval we're talking about, okay, that is equivalent to x minus a, and then we let this difference x minus a as our h. So this is our interval h. So the average, so when we speak of average rate of change, so we have the change in the y value divided by this one, the interval. So over that interval to the change of x. Okay, so our interval is h. So you divide the amount of change by the interval which is h. So that becomes our average rate of change. Okay? So I hope it's clear, class. Now, as we already know, for the amount of change formula, so as we already know, the instantaneous rate of change of f of x at a is its derivative, and is given by this. Okay, so remember this instantaneous rate, right? So the instantaneous rate of change of f of x at a is its derivative, and is given by this formula. F prime of a equal to the limit of f sub a plus h minus f of a divided by h. as h approaches to 0. So for small enough values of h, so it means, class, that as we move q very close to p, so what will happen is that our h, because as q moves here, h becomes smaller. H is the difference between x and a, x minus a. So this becomes smaller. So in this case, as point q reaches here, so our h is this one, very small. This becomes our h, very small, where h is the difference between x and a. So x minus a, this is our h. Alright, so if for small value or small enough value of h, f sub a, f prime of a can be approximated to f sub a minus f of a divided by h. So we can then solve for the f of a plus h to get the amount of change formula which is given into this. Okay? So we have f sub a plus h approximately equal to f of a plus a prime of a times h, or it can be also written as f sub a plus h approximately equal to f sub a plus, you can write h first, f prime sub a. Okay? They're just the same. Alright, so thank you, and in our next video I will solve some example, class, an application of this discussion. Thank you very much. See you in the next video. Bye.